Hi everyone, so today I'll be going through the networks and decision mathematics section of the 2017 Further Maths Exam 2. So question 1, bus routes connect 6 towns. The towns are Northland, Opera, Palmer, Quigley, Rosebush and Seatown. The graph below gives the cost in dollars of bus travel along these routes. Buyer lives in Northland, and he'll have to travel to take a holiday in Seatown. Buyers considering travelling by bus along the route Northland, Opera, Seatown. How much would buyer have to pay? So he's gonna go through Northland to Opera, then to Seatown. So we know that these represent the cost. The numbers on the edges represent the cost in dollars. So cost him $15 to travel from Northland to Opera, and then $105 to travel from Opera to Seatown. So 105 plus 15 is how much you'd have to pay, which is $120. So therefore, that's how much you'd have to pay. B. If buyer takes the cheapest route from Northland to Seatown, which other towns will he pass? So this is basically just trial and error. You just gotta try look for the cheapest route from Northland to Seatown. So basically you can do 30, 40, 30 over there, which is 100. Or the other option could be Dijkstra's algorithm, but that would be quite time consuming for the second question on the exam. So I'll just do it by looking at it. So that would be 100, 30, 20, another 30. That's 70. No, that's 80, sorry. And another route could be 30, 60, which is 90, so that's more. And I would avoid using into O because all the paths seem quite expensive down this route. So it appears to be that AD looks like the cheapest route from Northland to Seatown, so therefore $80 is the correct answer. Euler's formula, V plus F equals E plus 2. So V is vertices, F is faces, E is edges. Holds for this graph. Complete the formula by writing the appropriate numbers in the boxes provided below. So basically, we just count the number of vertices. So 1, 2, 3, 4, 5, 6. 6 vertices. So put 6 in there. Faces. Count the number of faces. 1, 2, 3, 4, 5, 6. And you always got to remember there's one face on the outside. So 7. And now you got to count number of edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. Now you can check if this is true. 7 plus 6 is 13. 11 plus 2 is 13. Therefore, you know your answers are right. Question 2. Buyer joins his friends Agatha, Colin, and Diane when he arrives for holiday in Seatown. Each person will plan one tour that the group will take. Table 1 shows the time in minutes it would take each person to plan each of the 4 tours. The aim is to minimize the total time it takes to plan the 4 tours. Agatha applies the Hungarian algorithm to Table 1 to produce Table 2. Table 2 shows the final result of all her steps of the Hungarian algorithm. So this is the table that has been produced after the Hungarian algorithm has been performed to this table over here. So in Table 2 there is a 0 in the column for Colin. When all values in the table are considered, what conclusions about minimum total planning time can be made from the 0? So you should know that after you complete Hungarian algorithm, the zeros are tasks that the friends over here could complete, the tours that the friends could complete. So for example, these 2 zeros suggest that Agatha could complete tour 3 or tour 4. So if we look at Colin, he only has 1 0, so that means Colin can only complete tour 2. So we can say that Colin must plan tour 2 in order to achieve the minimum completion time. And you could put it in brackets. It takes him 8 minutes to complete tour 2. Determine the minimum total planning time in minutes for all 4 tours. So to do this question, we can use this table over here that has the Hungarian algorithm completed to actually determine the total planning time, the minimum total planning time for all 4 tours. So we've concluded that Colin must complete tour 2. Now, if we have a look at Diane, we can determine that she can either complete tour 2 or tour 3, but since Colin has already completed tour 2, that means she can no longer complete tour 2, so she can complete tour 3. Now, if we go to Agatha, we know that she can complete either tour 3 or tour 4, but we know Diane is completing tour 3, so therefore we know she'll complete tour 4 then. And then Bai can either complete tour 1 or tour 4, but we know that Agatha is completing tour 4, so therefore Bai is going to complete tour 1. So now we're going to determine the minimum total planning time minutes for all 4 tours. So basically we know we can find the total completion time that each person's going to take to plan the tour by looking at table 1, which has the minutes. So we know Bai is going to complete tour 1. We know Agatha's going to complete tour 4. We know Colin's going to complete tour 2. And we know Diane is going to complete tour 3. Now, if you add all those minutes up, so if you add 10 plus 7 plus 8 plus 18, they'll give you the minimum total planning time in minutes for all the 4 tours, which is 43 minutes. Question 3. While on holiday, the 4 friends visit a theme park where there are 9 rides. On the graph below, the positions of the rides are indicated by the vertices. The numbers on the edges represent the distance in meters between the rides. Electric cables are required to power the rides. These cables will form a connected graph. The shortest total length of the cable will be used. Give a mathematical term to describe the graph that represents these cables. So you should know that electrical cables usually reflect the further maths concepts of minimum spanning tree, and we know that it's going to form a connected graph. And the definition of a connected graph is that each vertex can be reached via a pathway. It doesn't have to be directly connected, and the shortest total length of a cable will be used. So therefore, it's a spanning tree, but it's a minimum spanning tree because the shortest total length of cable will be used. So therefore, the answer is minimum spanning tree. Draw in the graph that represents these cables on the diagram below. So what I'd do is just start off with the smallest edge and then try build along from that so that each vertex is connected by another edge. So from 50 we look for the smallest edge around it, which is 100. And then from either 50 or 100 we can look for the smallest edge that's around it, which is 100. And then from 100 we can look for the smallest edge that's around it. It's 150, but we wouldn't connect that to there because then you're forming a loop, and we know trees can't have loops. It's just the minimum length of the cables that can be connected so that all the vertices are connected by at least one edge. So we would go with 200, which is the next smallest. And then we know that 150 must be connected to this vertex over here because we know that all the vertices must be connected to another vertice via an edge, and that's the only edge we have to use. And we know this vertice must be connected to either this one or this one. So we know that 300 is smaller, so therefore we would go with 300. And therefore, from this vertex over here, the smallest edge connecting it is 400, and therefore we only have one option for this vertex over here, so 200. So therefore, that is your minimum spanning tree. Question 4. The rides at a theme park are set up at the beginning of each holiday season. The project involves activities A to O. The director network below shows these activities and their completion time in days. A. Write down 2 immediate predecessors of activity I. So activity I is over here. We know that D is an immediate predecessor because it's immediately before activity I, and the dummy activity suggests that activity E is also before activity I, so therefore D and E are the two immediate predecessors of activity I. BI, the minimum completion time for the project is 19 days. There are two critical paths. One critical path is A, E, J, L, N. The other, write down the other critical path. So basically what I did was just complete the whole critical path analysis. And if you do need help with that, just leave a comment down below and I will try to help you as soon as I can. So basically if we look from what we have over here, we know that the critical path is A, E, J, L, N. And to do this, you just highlight the earliest and latest start times have the same number. So the first critical path that they put down was A, E, J, L, N. There's another one you can do, which we can see if so A, E, and then if you go use the dummy activity to connect up to this one and use I, it also results in the same completion time, so that is also another critical path. So therefore the other critical path would be A, E, I, it's shown here, I, L, N. Determine the float time in days for activity F. So I've completed the critical path analysis. So for activity F, you look to the box that is the left of the edge for F, and the float time is basically the latest start time minus the earliest start time. So latest start time is 11 and earliest start time is 5. So 11 minus 5 gives us 6. So therefore the float time is 6 days. For C, the project could finish earlier if some activities were crashed. 6 activities B, D, G, I, J, and L can all be reduced by 1 day. The cost of crashing is $1,000 per activity. What is the minimum number of days in which the project could now be completed? So you should note that they all cost the same to crash and they could all be reduced by only 1 day. So up here I've highlighted B, D, J, I, L, and G. These are the activities that can be crashed. So we want to find the minimum cost, the minimum number of days in which the project could now be completed. But the second question also says the minimum cost. So we'll try to find the minimum number of days in which the project could be completed at the minimum cost as well. So first step, so the first two activities we could crash are I and J. It's because they are both on the critical path, and if we want to reduce the minimum completion time, we first need to reduce the activities on the critical path. So you notice that if we reduce each one by 1, it becomes 11 here and 11 here. So 11 plus 5 plus 2 is now 18, but we still have L as an option to crash and G as an option to crash. So if we crash L by 1, that would be 4. So that will result in 11 plus 4, which is 15. And if we crash G by 1 over here, that's 8. So then it will result in 7 plus 8, which is also 15. So D would have no effect because D is not on the critical path. And if you reduce D by 1, that will become 6. So that will become 8 over here, and 8 plus 3 is 11, and that has no impact there. So you wouldn't crash D if you want to find the minimum cost as well. And B also has no effect because if you crash that to 2, it will become 2 plus 2 is 4, 4 plus 3 is 7, 7 plus 3 is 10. That's also 5 less than 15, so that would also not be there. So therefore, we've crashed 4 activities, which is also, and that would result in the minimum completion time. So 15 we've concluded is the largest number. So 15 is the largest number, and 15 is the largest number from here. So 15 plus 2 is 17, and therefore the new minimum completion time is 17. So therefore, CI, what is the minimum number of days in which the project can now be completed? We've concluded that 17 is the new minimum completion time, and it's in days. And then it also says what is the minimum cost of completing the project in this time. We know that it costs $1,000 to crash each activity. So we've crashed 1 activity, 2 activities, 3 activities, 4 activities. So we know it costs $1,000 each. So 4 times $1,000 for each activity crash is $4,000. So therefore, that is the minimum cost of completing the project in this shorter time.